This is section 4.3, part 6. We're solving by elimination. We have solved by using graphing. When we graphed, we talked about two special cases. We talked about how we could end up with parallel lines, and since they never cross, we don't get any solutions. We also talked about how it's possible that you have the same line, and in that case, you have infinite solutions. We need to talk about how you would recognize those if you're using the elimination method. So I've just given you a big clue as to what these answers are going to be. Let's look at this system right here. And we want to get rid of either x or y. Now we've been getting rid of x a lot, so let's just choose to get rid of y here, just because. Look at your 2 and your 4. Now this is what I meant by sometimes you have a nice pairing of numbers. I can easily turn the 2 into a 4 by multiplying it by a 2. And then I wouldn't need to multiply this by anything. It would already be exactly what I needed. But this is a -2, this is a -4, so I'm going to have -4 and -4. I need a +4, so I'm going to force it by making this a -2. Multiply everything here by -2. You would get -10x plus 4y is equal to -6, and I'm recopying the second one. If I add these together, what happens is my y's go away like I wanted them to, but the x's go away as well. So I have nothing left on the nothing remaining on the left-hand side, so that's a 0. And you do need to keep going, even though you know right here this is a big clue that something weird's happening. -6 plus 5 would be -1. Okay, so you know you have something weird because your variables canceled out. Now you need to decide whether you have parallel lines or if you have infinite solutions. And what you do is you look at what you have right here. Does 0 equal -1? This is false. 0 does not equal -1. So if your variables cancel out and you get something that is false, then what you have is you have parallel lines. So this is no solution, and this is inconsistent. Okay, look at the next one. What we have is something very similar. We want either our x or our y to go away. You can easily change the 6 into an 18 and the 3 into a 9. Just pick one. So let's say we want to get rid of x. I would need to multiply this by a 3. That would give me a +18 here, a -18 here. So go ahead and distribute this all the way through. 18x plus 9y is equal to, you are multiplying the 3 times the 0. It's just you get 0. Recopy the second one. And just like on the one above, both variables go away. So that leaves me with a 0 on this side. And over here we have 0 plus 0 is 0. Okay, so our variables cancel out again, so we have something weird. But we got something here that is true. 0 does equal 0. If your variables cancel out and you end up with something that is true, then you have the same line. And then that means they are dependent. And we're going to have to write our answer in set builder notation. Remember, they provide you with this set of all x, y, such that, and we have to fill this part out in standard form. So I need to look at one of these two equations and see, maybe it technically doesn't matter which one, but pick one of them that's closer to standard form. And I like this one better because the numbers are smaller. And we need to ask ourselves if it's in standard form, and if it's not, what do we have to do to make it better? First requirement is that you have x and then y equal to a constant. We have that. Our first number has to be positive. We have that. We cannot have any fractions. We're good there. And it must be quote unquote reduced. There is something that divides evenly into 6, 3, and 0. It has to go into all three of them, and each of these is divisible by a 3. So you must do that. 6 divided by 3 would be 2x, plus 3 divided by 3 is 1, y. 0 divided by 3 is 0. You can have a 0 on the top of a division, you cannot have one in the bottom. So what needs to go right here is 2x plus y equals 0.